Hi again, guys. So we talked in our last video about motion. And one of the things that we said is that when you go through some distance or displacement, that if you go through that displacement over time, we can determine what your motion is. Today what I want to talk about is what happens when motion changes. So for instance, if you're walking along and you're covering the same distance every second, we would say that you have a constant speed. In that case, if you're going in a straight line and your speed is not changing, you don't have any acceleration. Right? There's no acceleration if your speed remains constant and your direction also remains constant. You guys should remember that from the last video. However, what I want to talk about today is what happens if my speed is not constant? What happens if it changes? All right, if my speed or my direction changes, I have acceleration. All right, that means I'm accelerating. So you can see a lot of examples of acceleration. You've experienced many of them. If I am at a stop sign in my car and I take off, my speed will change. That means acceleration has occurred. All right? If I'm standing on top of the roof and I decide I want to jump off, my speed's going to change. I went from not moving at all to, as I fall, I'm speeding up more and more and more every second that I fall downward. So falling is an example of acceleration. Taking off from a stop sign is an example of an acceleration. If you're sitting in your chair at home and you get up to go get a drink, guess what? You went from not moving to moving. We accelerated. So in today's video, what we're going to do is we're going to look at acceleration. And what you'll notice is that sometimes acceleration is really, really high, and other times you may hardly even notice it. All right, so what we've seen here then is that anytime that something changes its speed, that we have an acceleration. I think that's fairly easy to see. We've all experienced this. You may have been sitting in your car just minding your own business, and maybe one of your parents drives where they like punch the gas and you kind of feel like, whoa, the car's going fast, and you get slammed into the back of your seat. Or they wait to slam on the brakes until the last minute, and so you kind of feel yourself going forward. You're just trying to keep doing what you're doing, but you're experiencing an acceleration that's making you change. Okay? But it's not just speeding up and slowing down. If you envision, and maybe you played that game when you were a younger kid, you go on vacation somewhere, you got your little brother sitting next to you, and your mom or dad take a curve in the highway, and you're going fairly fast, and you kind of like feel like you're getting pushed to one side. See, if you do circular motion, you're also, even if your speed doesn't change, even if you take that curve at the same speed all the way around it, because your direction changed, you accelerated then too. So circular motion is also going to have acceleration because your direction changed. Remember, velocity has both a direction and a speed. If you change either one of those two, or both, you're going to have an acceleration. All right, so we've established then that anytime you have a change in speed or a change in direction, or both, you're going to have acceleration. But there's one more part that goes into acceleration. You see, let me give you an example here. I would have an acceleration if I'm driving down Austin Road outside of town and I see the stop sign coming up, and so I'd slow down. So let's say I'm going from 50 miles an hour down to 0 miles an hour. So I would have a particular acceleration in doing that. But I could also have the same change in speed if I wasn't paying attention and I was looking at my cell phone or whatever, and I drifted off the road and ran into a telephone pole. I would have the exact same change in speed. I'd go from 50 miles an hour to 0 at the stop sign, or 50 miles an hour to 0 by hitting a telephone pole. Now, the feeling that you would experience inside that car would be dramatically different depending on how long it took to have that change in speed. So same change in speed, but dramatically different acceleration if I'm slowing to a stop at the stop sign versus running into a pole. All right, so it's not just how much your speed changes that determines your acceleration. The other thing that determines acceleration is how long does it take? So we already looked at our variable for time when we talked about velocity. It's basically just delta t, the change in time. And so knowing these two things, this kind of allows us, by the way, the speed change we can write as delta change in velocity. Okay, so if I look at an acceleration then, both of these determine what the acceleration is. And so what we want to look at now is, let's see if we can't figure out how to make a formula out of these. And the way that we do this, we kind of use some symbols that may look a little bit strange to you. But we're going to say that acceleration is related to these two factors. So in some way, it's related, these two factors are related to acceleration. And we use this funky symbol that kind of looks like this. And what this means is it's proportional to. Now there's two ways that acceleration can be related to these two things. One is if speed increases, so does acceleration. The other possibility is if that speed change increases, acceleration goes down. So we would say that acceleration's either directly related to speed change. Again, that would mean that if I get a big speed change, I get a big acceleration. The other alternative is if I get a big speed change, I get a smaller acceleration. That would be indirectly related. Think about this one. If I get a big speed change, do I have a bigger acceleration or a smaller one? Well, the fact is, the bigger the speed change is, the more acceleration I get. Okay, so they're what we call directly related. And so I would say that acceleration is directly related to my change in speed. All right, that's what delta V is the change in speed or velocity. Okay? Now, let's think about this, though. How is acceleration related to, so we're going to use that little symbol again, how would it be related to time? So think about this. If the acceleration takes a really long period of time, all right, if my change in speed takes a long period of time, would I have a big acceleration or a small one? Think about it this way. A big acceleration, like if you're in a car, a big acceleration means, man, I really feel like I'm being thrown forward, or I really feel like I'm being pressed into the chair. All right, now when you first learn to drive, you probably jam your brakes on, which means you kind of feel this feeling that you're going forward. The reason? You had a change in speed and it didn't take very long. So delta t was small, which meant acceleration was big. I would really feel it. All right? Sometimes maybe you punch on the gas, and so to go from 0 to 50 miles an hour doesn't take very long. The smaller that time is, the bigger that acceleration is. Now, that's not the same relationship that we saw here. So what this means is acceleration is not directly related to time. It's indirectly related to time. The way we handle that is we would say acceleration is related to 1 over delta t. This is how they make these formulas. They think about what the relationships are, and they basically say, okay, if this is the relationship, I might be able to get a formula from this. All right, so what would this mean? The bigger that this number is, let's just say it took me 1 second to undergo a certain change in velocity. Well, my acceleration then would essentially be 1. 1 over 1 is 1. But what if it took 10 seconds? Well, then it would be 1/10, which would make my acceleration much smaller, 1/10 of what it would have been. If I combine both of these, you guys, we get a formula for acceleration. You don't really need to remember this, but this is how they do it. What you should remember is this: an acceleration formula is going to equal delta V, that's a mess, over delta T. All right? This is a formula for acceleration. Okay? This is a formula for acceleration. You don't usually use this form of it. Usually what we do with acceleration, and I'm just going to write this as a lowercase a, that usually means acceleration, equals, we're going to expand this. And you might remember from yesterday's video, delta anything is the change that occurs. And we can expand delta V by saying the final velocity, how fast it's moving at the end, minus the initial velocity all over delta T. This formula right here, you guys, is going to be one that we're going to come back to over and over and over again. But this is the formula for acceleration. Okay? If you guys have your comp books, this is another formula. It would be a good idea to write this in the back of your comp book, and you're just going to label the formula acceleration. All right? This is going to be the one that we come back to over and over. All right, you guys, so we're going to take a few minutes to kind of work through a problem that we have here. One of the reasons I want to work through a few of these with you, I think you're going to see mathematically it's not too bad. But I want to work through one of these with you so I can kind of get you used to the way that I want you to solve word problems. So the very first thing, and you may have solved word problems in your math class before, and you may not really like them. But I will tell you, I'm going to teach you guys some strategies where you shouldn't ever have to fear a word problem again. I know some of you guys get them in math, and you're like, oh, you just skip it. So to avoid skipping it, because you're going to see some word problems, to avoid skipping it, let's just think it through, and we're going to do it very systematically every time. The first thing you do, read it, and you're not just reading the question to read. I know sometimes you guys do that. Okay, so I can say, oh, I read it. Understand, visualize is what I would tell you. Try to envision, what are they describing for me? Okay? So this one says, your car slows down from 20.0 meters per second to 0.0 meters per second. All right, so what am I envisioning right now? What's occurring here? My car was traveling at some speed, and then it comes to a stop. All right, so maybe there's a stop sign that I'm approaching, something like that. But that's what I'm envisioning. If this took 4 seconds, what would be the acceleration of your car? All right, so we're going to calculate acceleration. But we kind of are understanding here that our car is slowing to a stop, and we want to know what the acceleration is. Now what I'm going to do, I've read it, I kind of visualized what's going on here. The next thing that I want to do is I'm going to reread it. This time, though, I'm looking for particular variables. All right, what do I know? I usually tell people, what do I know and what do I not know? All right, sometimes what I don't know is almost as important as what I do. So as I reread, your car slows down from 20 meters per second to 0 meters per second. So what is 20 meters per second? Usually you run into a number and you figure this has got to be something. Well, clearly, and these units are your friends, don't ignore them. Meters per second, distance over time, This is always going to be a velocity. My issue is that I have two velocities here, and one of them came before the other. This is why visualizing what's happening is really important, because this allows us to distinguish what was the first velocity and what was the last velocity. If it went from 20 to 0, then my initial velocity, the speed I was going at in the beginning, we'll call that VI, it was 20 meters per second. Okay? Do include the units. Then if that was what I started at, but this is what I finished with, what would 0 be? Well, 0 must be then, if this was the initial velocity, VF is going to be the final velocity, the speed I was moving at the end. Okay? So again, in my head, I got this car, it's moving along, it's going this speed, it slows down to 0. If this took 4 seconds, what are they asking me for here? Or I shouldn't say what they're asking me for. What information are they giving me here? Again, look at the units. Measure in seconds. I measure time. Guess which variable this is? This is going to be delta t. All right, my delta t is 4 seconds. Don't forget these units. I'm going to tell you guys, when I start grading your homework, I'm going to look for these. I want to know that you've identified what you know and what you don't. Because 9 times out of 10, if you're missing something, it's going to be in here. So by looking at what you know and what you don't, I know exactly how to help you guys fairly quickly. That's why I want you to write this down every time. What would be the acceleration of your car? This is the question, right? This is what they're asking me. So which variable, again, these are all variables, which variable are they asking us for? They're asking for acceleration, which has the variable lowercase a. So I'm going to say a down here equals, and I usually just throw some question marks in there. I don't know what it is. Okay? So once I've identified what I know and what I don't, I just need to pick out a formula that will only have one thing that I don't know. All right? In our case, I don't know acceleration. I don't know what it is. And so I want a formula for acceleration. Well, lucky for you, you only have a few formulas right now. But I know by looking at the formulas that I have, the only one that has a in it, which I need to solve for, is the acceleration formula that we just looked at. All right, it's going to be VF, I have it, minus VI, I have it, over delta t, I have it. So I have all of these, the only thing I need to know is A. Okay? So at this point, I don't even really have to do any algebra with this. I don't have to move any of these variables around, which is what a lot of physics students struggle with, is really just the simple math of moving variables around. I don't have to do anything because the thing I want to know is already isolated. I can go ahead and plug in numbers. One thing before I plug in numbers, though, that you always want to check, make sure your units match. If the units here don't match each other, so for instance, all the times are in seconds, all the distances are in meters. If they don't match, you're going to have to convert something to make a match. All right? You can't subtract one number from another if this is in miles per hour and this is in meters per second. You can't do that. They have to be the same. They are all the same. We can go ahead and plug in. My VF is 0. Meters per second minus my VI, which was 20 meters per second. And my time here was 4 seconds. My delta t is 4 seconds. So if I simplify this just a little bit, if you look at the top, be real careful here. This is 0 minus 20. So this is going to be negative 20 on the top over 4, positive 4 seconds on the bottom. Okay? So this math is not too tough. If I take negative 20 and I divide it by 4, I'm going to get negative 5. I'll get into the unit in a second, but let's think about significant figures. All right? Here I'm dividing. The major operation here is dividing. I want to figure out then, if we're dividing this number, which of the numbers have the least number of sig figs. That would be delta t. 2, although I accidentally wrote it with 3 here. Let's get rid of that. All right? If this only has 2 sig figs, I'm only allowed 2 sig figs in my answer. So I can't say 5.00. I can only say 5.0. That 0 is significant because there's a decimal in the number. The unit is kind of weird. Now, I know in math class, you guys probably do this. You do a calculation or something, you get a number that's at the end, and then what do? You just say, well, what unit should be there? I don't want you to do that. There are certain units that go with certain values. So for instance, velocity, I already talked about it, always meters per second. Could be miles per hour, but it's always distance over time. Delta t is always hours, seconds, days, that kind of thing. Acceleration has a unit, and its unit is meters per second per second. Now that looks like a really weird unit. The way we usually write it, though, is meters per second squared. Okay? This is always the unit of acceleration. Let me try to explain this. Remember that acceleration is the rate at which velocity changes. Okay? So we said it was basically delta v over delta t. I showed you that earlier in the video. So all we're saying is the speed, which is in meters per second, changes by a certain amount each second. So we'd have units of meters per second per second. It's the rate at which your speed changes. Well, we shorten that to this. Okay? So if I look at my units, this would be meters per second, but that second in the denominator here would actually drop down with this one. So I have meters per second times seconds, or meters per second squared. That is your answer for this particular question. Okay, you guys, one more example today. This one's going to require us to move some stuff around, but you're going to follow the exact same steps that I did in the first one. Remember, the first thing you want to do, read the question, and you're reading to understand the situation more so than the numbers. Okay? You're traveling at 25 meters per second, and you see a cat in the road. Your car can accelerate at negative 8 meters per second squared. Now, let me talk about this really quick. If you have a negative acceleration, what it actually means is you're slowing down. All right? A positive acceleration means I'm speeding up. A negative one means I'm generally slowing down. Okay? So when you see this negative, that's all it means. It just means I'm slowing down, not speeding up. How long will it take to stop? Okay. So this one's a little more challenging than the last one, but hopefully you're envisioning what's happening here. You're driving along, and you're moving at 25 meters per second. You see a cat. You're going to slam on your brakes. Don't mistake accelerate, meaning you're going to go faster. I hope that's not you. Speed up to hit a cat or anything. But the fact is, even negative accelerations are still accelerations. Again, because it's negative, it just means you're slowing down. All right, so I'm going to jam on my brakes in order to experience a negative acceleration. And it's wondering, how long do I have to come to a stop? Okay, how long will that take? So now that we've read it, we understand the scenario, we want to start assigning variables. You're traveling at 25 meters per second. So if you look at the unit, let them be your friends. They're going to tell you what they're describing. If you see distance over time, meters per second, this is a velocity. All right? The question is that your first velocity or your last velocity? If you've envisioned this question already and it's in your head what you're doing, this is your initial velocity. And so I would say VI equals 25. Oops. I'll leave the decimal there. It has the same number of sig figs. Meters per second. Could you guys tell me what your VF is at this point? Could you tell me what your VF, your final velocity is? They did not come right out and tell you in this question, but they did give you a clue. It says at the bottom, how long will it take to stop? Well, how fast is stopped? Stopped is 0. So we would say our VF is equal to 0.0 meters per second. The truth is, you guys, stopped is stopped. There really are no number of sig figs that we need to put here. It's an infinite number of sig figs. You're either moving or you're not. If you're not, you could say this is 0.0000 and just go all the way out to infinity. I'll just stop with 2. All right? What else did they give us? You're traveling at that speed. You see a cat. Your car can accelerate at negative 8.0 meters per second. Variable they're giving me here, you guys, is acceleration. How do I know? Well, 2 reasons, really. For one, it says it's accelerating. The second thing is I look at the units. Remember the last question I told you, the units for acceleration are always meters per second squared. So the fact that that has that unit attached to it means it must be an acceleration. So this is negative 8.0 meters per second squared. And then finally they ask, how long will it take to stop? How long will it take? All right? If I were to ask you, how long will it be until you're ready to go to the store? You're going to answer me with a time. 5 minutes, 10 minutes, 20 minutes. All right? How long is time? And so what they're asking me for here is delta t. All right? They're asking me for delta t. So what they've given us the 2 velocities, the starting and the ending, and they've given us the acceleration. What they're asking us for is, how long is it going to take? Now, if you look at the formulas you have, the only formula that you have that has a in it, and where there's only one missing thing, is that acceleration formula that we've already looked at, which is a equals VF minus VI over delta t. Now, why is this a little more challenging than the last question we looked at? Because I have to do a little bit of algebra to this in order to solve for delta t. All right? Right now, this delta t is on the bottom of this fraction. And you guys hopefully learned in math that you always have to isolate the variable that you want to solve for. When I was in math, if I didn't hear isolate the variable a million times during that year, when I took Algebra 1 essentially, I can't imagine hearing something different here. This is just automatically what you do. So how am I going to isolate delta t? I need to get it by itself. Well, when you get good at algebra, you just kind of do this. If you're struggling a little bit, the first thing I would want to do to isolate delta t is I want to get rid of the fraction. When I have fractions, I make mistakes. So the first thing that I would probably do here is I want to get this delta t out of the bottom of this fraction, and I would do that by multiplying both sides by delta t. So we're going to do a little bit of Algebra 1 here, okay? Now, what would that do on this side? Well, delta t is going to cancel out that delta t, and I'd end up with this, okay, with VF minus VI, because these two would cancel. Over here, I've got delta t times A. So I've gotten rid of the fraction at this point. You know, I'll rewrite this. I'll just say this is A delta t equals VF minus VI. Okay? Now, the problem is, I've gotten rid of the fraction, that's great. But the problem is, I haven't isolated delta t yet. So unfortunately, we're going to make a new fraction here, but we're going to do it so we get delta t so it's by itself. To do that, I'm simply going to divide both sides by A. If I do this, A cancels on this side, I'm left with delta t. And we can say that delta t equals VF minus VI over A. Now, how am I going to know that I did this algebra correctly? It's in the units. You guys will see in just a second. So I can plug in now to my formula since I've isolated delta t. I can plug into my formula, but remember, there's something you got to do before you do that. Double check your units. Make sure they match. Meters are my distances. My times are all in seconds. So we're good. All right? Our units, I don't mean they have to be the same units. I do mean that the distance unit has to match. The time unit has to match. Okay? So we're good to plug in. My VF, 0. Minus my VI, which was 25. All right? A was negative 8.0 meters per second squared. Okay? If I simplify this, delta t then is going to equal, on the top, negative 25 meters per second, divided by negative 8 meters per second squared. The way, again, I want you to envision this second squared, it's basically seconds times seconds on the bottom here. If I do this math, I should have used a different number. I've got to do this in my head now. This is going to be 3.125, I think is what it's going to be. I just got confirmation. So this is going to be 3.125. Positive or negative? Well, if I have a negative divided by another negative, they'll cancel each other out, and this should be positive, which makes sense. Delta t can't be negative. You can't go back in time, all right? You can only go forward in time, and so it's going to be positive 3.125. We'll get to the sig figs in a minute. What about our unit? Well, this meter is here, and this one's here, and so they're both opposing each other. They'll cancel. This second that's here in the denominator of this fraction is opposed to these seconds that are in the denominator of this fraction, which means one of these is going to get canceled. Remember, you need to think of this as seconds times seconds. Here, that's what second squared is, so that second's going to cancel one of those. What I'm left with is a unit that is basically 1 over seconds. So seconds would be way down here. Well, you might remember if you divide by a fraction, you multiply by its reciprocal. I know it's complicated, but trust me, you'll get used to it. So basically, this seconds that's left down here becomes the unit of the numerator. Now, you want to ask yourself, would that unit make sense? Would it make sense to have a unit of seconds if I'm solving for delta t? Sure it is. Why would I want to do that? Why would I bother? If I get the right unit here for delta t, it means that my algebra was probably correct. If I get some funky unit here that doesn't really go with time, then I probably messed something up here. This is a check on your math, you guys. You will not miss questions due to algebra if you work the units all the way through and you end up with the right unit. It's not something you just throw on at the end. All right, last thing here, sig figs. Do I have the proper number of sig figs? If I look over here, that has 2, that has 2. I am not allowed to have 4 like I do right now. We're going to have to round this. Here's the first one, here's the second one. I look to the 2 to see what I need to do with this 1. It's less than 5. So I would round down, not up. My answer here is going to be, and you could say it's positive if you want to, but it's understood. This is going to be 3.1 seconds. So basically, our time for stopping is going to be positive 3.1 seconds. All right. So that is it for this initial look at acceleration. We're going to see that acceleration really plays into a lot of the stuff that we do. So your ability to determine acceleration is going to be fairly important going forward. You guys are going to work on some problem sets in just a minute. If you have questions or if you have trouble, I know a lot of you guys might struggle a little bit with the algebra based upon my previous experience. I've been doing this like 20 years plus. And so when I see the mistakes people make, it's usually in here. If you need help with that, pop back into the Zoom room and we'll talk about it. We'll get it fixed, okay? All right. So this is basic acceleration, and I will see you guys in the next video.